have two fairly similar situations, but I want to point out sort of the differences. We have two charges, Coulomb 1 and 2, and over here, when we want to find the force, we use Coulomb's law and we find the force on this charge, force on whatever charge this is, on our Q that's just hanging out over here. And that's a vector, right? And so that would point in, right, this would be pointed like this. That would be the force from 1, and then the force from 2 would go down this way. And I don't know which one would be bigger. Over here in X marks the spot, we would find the electric field at this point, at X. And it does the same thing, right? That's the electric field. We find this electric field, and that tells us what happens once we put our Q in, but there is no charge here, okay? So, and our connection between these two is, of course, this force is equal to Q times E, whatever Q we have sitting over here, okay? That's the vectors and the electric fields. Now, in terms of energy, we can find the potential energy of Q, or over here, we can find the electrostatic potential, this voltage. And so to find this, that would be, in this case, it would be K, or Q, Q1 over R1, where this would be R1, right? Plus K, Q times Q2 over R2. Beauty is there are no vectors here. We just add them up. The voltage at this point is just going to be K Q1 over R1 plus K Q2 over R2, right? So this works the same. It just tells us what happens when we're going to put a charge in here. And so again, our connector is that U, the potential energy, is Q times V, where we've assumed the reference point. Notice what's implied here is that our reference point is that U equals 0 or V equals 0 when R is very far away, when this charge is really far away. And we got to this expression by saying change in potential energy equals minus the work, and the work was, right, this integral of F dot dr, or our change in potential is equal to minus F dot dr. So over here, our change in the voltage is equal to minus E dot dr, okay? So the thing that's nice about voltage is we can just add these numbers. If we know this distance, R1 and R2, we can just add them. There are no vectors. Remember, when we had to do this, we had to say, well, we got to find the components of this, the X and Y components. So this is a lot easier. And so sometimes we can start with the electric field and find the voltage this way by taking the integral. But sometimes if we've just got some individual points, it's actually easier to go like this. Okay, so one situation where we had looked at, like if I have something of 12 volts to 0 volts, here, the way we set this up is we set up a plate, as it turns out. This is one way we can set it up, to set up a plate where we have lots of positive charges and the same number of sort of negative charges here. And we can set up, it turns out this can give us a uniform electric field. There's our electric field like this. It's a constant value all the way through here, and we can find, in fact, that this change in voltage is equal to minus the electric field times whatever displacement. So if we call this sort of our 0, and this is some distance d away, so we have 0 volts at 0, then we could say if we're going from, say, from this point to this point, we can say we're going from d to 0 of E along the x direction, E dot x, right? Just like we're doing a work equation, E is pointing this way, X is pointing this way, so we don't have to have the dot product anymore. If E is constant, then this delta V is equal to then minus E integral d to 0 of dx, or this delta V is equal to minus E 0 minus d, or delta V is equal to, E times this little distance, or our electric field would be 12 volts over whatever this distance is, right? Because the delta V would be 12 volts. And so if we have a uniform electric field, then, and we know the voltage, which is this setup, then we can actually calculate this fairly easily. If this is 10 centimeters, this would be 120 volt difference across here, for example, 120 volts per meter difference. And so that is would be the right units for the electric field. Okay, so this would be the magnitude of the electric field. Okay, so that's just to try to keep you organized. I think it's useful to think about force and potential energy in terms of what's happening to a charge of interest. This electric field and voltage are what's happening in space, somewhere where something might appear.